Hello viewers, I am Kausalya. Today we are going to see a derivation about parallel resonance. So here when the elements are connected in parallel, then the circuit is said to be a parallel circuit. So regarding here, we are having R and L as one branch and R2 and C as the other branch. So these two branches are parallel to each other and they are connected across a voltage source E. So the first thing is we are calculating the admittance value. Therefore, the total admittance is given by admittance in this part plus admittance with this part. So it is denoted as YL and YC. So Y is nothing but it is the reciprocal of Z. So it is replaced with 1 by ZL plus 1 by ZC. Again, ZL is given by R1 plus JXL because in this part we are having R1 because in this branch we are having R1 and L. So it is written as R1 plus JXL. So when you look at this branch here R2 and C, therefore it is written as R2 minus JXC because of the capacitance here. So here the thing is we are just taking the complex conjugate here. So R1 minus J, that is we are multiplying this expression with its opposite sign. That is 1 into R minus JXL divided by R1 minus JXL. Therefore here R1 minus JXL divided by R1 square plus XL square, and here R2 plus JXC divided by R2 square plus XC square. Right. So again we are splitting this equation. We are splitting the denominator for the real term as well as for the imaginary terms here. So when you write the expression, how it will be, you see R1 by R1 square plus XL square minus JXL by R1 square plus XL square. Similarly, R2 by R2 square plus XC square plus J into XC by R2 square plus XC square. Right. And the next thing here is we are combining the real and imaginary terms separately. So this term are combined together. Similarly, this term and this term are combined together. Right. So what happens during resonance? At resonance, the reactive part of the impedance becomes 0. So here this part becomes 0 here. So just equate this part to 0. So what happens? We are moving this XL to the right hand side. So it becomes positive. And the next thing is we are doing a cross multiplication. XC gets multiplied with this term and XL gets multiplied with this term. And the next thing is we are introducing, that is we are introducing our omega naught, right? So XC can be written as 1 by 2 pi FC, right? The 2 pi F is replaced with omega naught here. Because this happens under resonance condition, right? Therefore omega naught. So 1 by omega naught C into R1 square plus this XL is omega naught square L square. And here it is XC is given by 1 by omega naught square C square. Right. So again I am moving this omega naught C to the right hand side. Therefore this becomes omega naught square LC. Again here what happens? I am moving this omega naught square LC inside the bracket. Right. So here I am getting an expression like this. Just we are doing random arrangements here. That's all. And again we are combining the omega naught terms together and we are combining the constant terms together. So here I am moving this term to the left hand side. Therefore that becomes minus. And I am moving this R1 square to the right hand side. So that becomes L by C minus R1 square. So here in the next step again you see omega naught square is taken outside. Right. And the remaining terms are here. So which is equal to L by C minus R1 square. And here the thing is I am multiplying both the numerator and denominator, multiplying and dividing this term with LC. Right. So when you do this, you see what happens. Here we are having an expression like this. Again when you rearrange the expression, you see we will be getting an expression as omega naught square is equal to L by C minus R1 square divided by this term. Okay. This LC into this part. So this is written here. So again when you rearrange, that is you see this LC is kept outside. So 1 by LC, and the remaining terms here just I am rearranging. That is, you see, I am rewriting this equation as R1 square minus L by C. In the same way, I am doing it in the denominator side. Right, so this becomes R2 square minus L by C. So here what happens? We are taking a minus outside from both the numerator and the denominator, and these two will cancel eventually. Right? And here the next thing is, again, I am writing an expression for omega naught. Okay, therefore square root is taken. So 1 by root of LC, then square root of R1 square minus L by C divided by R2 square minus L by C. So finally, this is our expression for the resonant frequency, right? Resonant frequency, that too for under parallel resonance, right? So in this, with the help of this above equation, we are going to reframe this equation for different conditions, right? So here the first criteria is, you see, if R1 is equal to R2, if both the values are equal, then here what happens, you see, this term and this term will cancel each other. Fine, because the values are same, and here L by C is same. So the value of omega naught will be equal to 1 by root of LC. Right, this is what written here. And again in the next thing, if both R1 square and R2 square are greater or less than L by C together, that is in both the cases. For example, now you consider this R1 and R2 are greater than L by C. So what happens? The output will be positive. Say yes or no. When R1 is greater than L by C, here the output is positive. Similarly, when R2 is greater than L by C, here this output is also positive. So when this thing is positive, what happens to omega naught? The answer of this omega naught will be real. Right, you will be having a real number. In the same way, when the value of R1 is less than L by C, what happens? Here the answer of this expression will have a minus sign. Similarly, when R2 is less than L by C, again this will produce a minus sign. So again this minus and minus will cancel out each other, and finally the value of omega naught is again a real number. Right? Am I making it clear? Yes. The next thing is, if the value of R1 is equal to R2, then what happens? You see, when the value of, that is this R1 is equal to L by C here. So what happens? Here the answer is 0, right? Similarly, when this R2 is equal to, that is R1, R2, that everything is equal, okay? So this term becomes 0, right? So when the value becomes 0, you see, if R1 and R2 equal to root of L by C. So root of L by C, when it is whole squared, what is the answer? That becomes L by C. So L by C minus L by C is 0. Similarly, here also it will become 0. Right. Therefore, what happens to the omega naught? 0 by 0. So it is indeterminate. Right. Now, the next condition is, when the value of, this R1 square is less than L by C and this R2 square is greater than L by C. So, you see, again look at this expression. When R1 square is less than L by C. When R1 square is less, what happens? This gives a minus sign. When this R2 square is greater than L by C, this gives a positive sign. Therefore, square root of minus sign, what happens? Square root of minus is nothing but an imaginary thing. Therefore, the value of omega naught is imaginary. Right. And finally, you see, to find the impedance at R1 equal to R2. When R1 is equal to R2, what happens? The value is equal to root of L by C, and omega naught is given by 1 by root of LC. Right. And the value of admittance is root of C by L, and the value of impedance is finally root of L by C. Right. So here comes the end of this derivation. If you have any doubt in the comment section, let me know in the comment section. Thank you.